Hey everybody, my name is Sam Epley. I am based out of the Twin Cities, just west of Minneapolis, Minnesota, in the United States. Today, what I'm going to do is walk through the Workout Wednesday 2022, week 42 of Can You Estimate Aaron Judge's Home Run Trajectories? Essentially, we're doing projectile motion and physics in Tableau. And for those of you where physics or baseball might not be big passion areas for you, I want to give a little bit of background on why I chose that as my challenge for this week's exercise. So, growing up, I grew up in a small farm town community in Iowa. From an early age, my favorite sport to play was baseball, and the reason for that is because you got to throw, you got to run, you got to swing a bat, and I was a pretty small kid growing up. So football really wasn't something I could do and be good at. Basketball, when everyone hit their growth spurts, I was one of the smaller kids. So, long story short, baseball was kind of the sport that I really closely followed, pretty much all the way until graduating high school. So, there's the fascination with baseball. Secondly, the fascination with physics. So my favorite subject all the way through school was mathematics. Took some college level courses when I was in high school, and I really enjoyed numbers. I was a part of the math team at my high school. And long story short, when I started taking a physical science class my freshman year of high school, that kind of opened my eyes to the television show Mythbusters, which I never heard of, and absolutely loved it. Loved watching episodes of that, testing out different hypotheses, and trying to understand not only the kind of the academic side, but also the practical example of it, of actually like, let's throw a ball and see how it behaves. Another television show that really inspired me to really kind of pursue a fascination with physics was sports science. And I think at one point in time it was associated with ESPN, and I just thought it was really, really fascinating how they would not only take the actual physical test of something, but then they could actually convert that and talk about the numbers behind it. So I thought that was really, really fascinating. And when you can see it kind of here, there's a little bit of an outline of a baseball diamond on my whiteboard. There was a Twitter handle that I stumbled across probably a couple months ago now, called Would It Dong. And Would It Dong is essentially measuring if a given hit in a ballpark in Major League Baseball, if that hit was replicated across all 30 of the Major League Baseball stadiums with a given exit velocity and launch angle, would it be a home run or not? Because in some ballparks, if you've got really close fences or interesting dimensions to certain things, certain hits could be home runs, other ones that could be flyouts, could be doubles. So that's kind of where a bit of that fascination came from, is trying to understand and do a test for, would a given hit be a home run? And that kind of spurred a thought when Kyle Yetter asked me several months back whether or not I wanted to do a Workout Wednesday challenge. And that's kind of what I decided that I would do, because there's a lot of great applications for Tableau as a business intelligence tool, being able to communicate insights with kind of the traditional charts and maps and different types of plots that are out there. But I wanted to do something a little bit different and a little bit more kind of on the edge of stretching the boundaries of what Tableau can do. And with that, I'm gonna walk through the challenge here, and I'm gonna share my screen. So, all right, so here is the challenge. So, part of the reason why I decided on Aaron Judge is because he's the first Major League Baseball player in the American League in more than 60 years to surpass that the record that was set by Roger Maris in 1961, where he broke Babe Ruth's record from, I think it was 1929 or 1931. And basically, I wanted to be able to see, can we model the path of flight of a ball over time? So with that being said, This is on a scale of 1 to 10. I'd say that this challenge is probably about a 9 to a 9.5. It is incredibly challenging, but it's also leveraging some pretty complicated concepts with physics, with drag coefficients, a bunch of different things kind of coming in. We're basically getting to the point where we're thinking about physics and we're thinking about calculus kind of in a way, because at each little time step that we're measuring, you have a different velocity, which then a different velocity by default that impacts the amount of drag on a ball at a given point in time. And I'm going to walk through this challenge to help you understand it. But this is what the end dashboard ends up looking like. It's got some summary KPIs here at the top: number of home runs, the average distance, average exit velocity, average launch angle, and average pitch velocity that's faced. And then there's 3 scatter plots here. One is measuring the relationship between the exit velocity of a ball and its distance. You can see that there's a positive relationship there with launch angle and distance. It's kind of a mixed bag there, not necessarily a clearly defined correlation. And then pitch velocity and distance, and there's not really much of a relationship there either. So the faster the ball comes off the bat, presuming it has a good launch angle and it's not not flying probably below 15 degrees, you're going to have a good chance that if you have a really well hit, really hard hit ball, that's going to travel quite a distance. So the bottom component here, that's where probably 80-90% of our time is going to be spent going through this challenge, because that is where we're getting into incredibly complicated physics calculations that I'm going to kind of talk through here. So dimensions: 1250 by 1000, 5 sheets, one that contains all 5 KPIs, 3 scatter plots, and then the trajectory plot. Got some formatting stuff there. And for the sake of this, probably not going to get super into that. But there's some bonus things here, making the balls be pointed in different orientations as opposed to just like one ball pointed straight up and down. And then when you play the play axis, then basically in Tableau public or in Tableau desktop, it's able to render it much faster than it is on the web. But what you're able to do is essentially see the ball look like it's rotating backwards, like it's got backspin as it's flying down its path. So that's part of the challenge that I wanted to incorporate in this as a bonus thing. But that's essentially what we got to work with here. So our data, I've got it hosted here on data.world, and there's basically 2 data files and then an image. So here we have the Statcast data in a CSV, and this details the number of the home run, date of the game, the opponent, whether the game was home or away, who the opposing pitcher was, the 2 big factors that we're going to be caring about, which is exit velocity and launch angle. Those are really the 2 critical things here. Hit direction, air density estimate. So the caveat with this is that the data that comes from Statcast, and I'll share it here on the screen. So this is by Baseball Savant as a part of MLB.com. What they have is they have the 2 major things that we care about, which are the exit velocity and the launch angle, and that's all fine and well. The challenge with it, though, is that if we think about how a ball moves and how like it's the different qualities around that ball, the rate of spin, the orientation, the axis that ball is spinning, all of those different factors, when we calculate it on a singular hit level, that will impact the trajectory and the curve of the flight. So to give you an example here, what we see is that this home run here hit 2 days ago by Aaron Judge. This was during a playoff game against the Cleveland Guardians. It's not a straight shot. The ball is curving in flight. And if you go down the rabbit trail of physics and YouTube, just Google search or YouTube search the whole concept of the Magnus effect. And that's what the Magnus effect is, in effect, what allows a curveball thrown by a pitcher, it allows it not to just curve normally based off of trajectory that you would see, kind of like I throw the ball in this direction and then it goes that way and then gravity pulls it down. That's one factor of curve, but that's due to gravitation. When a pitcher spins the ball at a high enough rate of speed, what happens is that it creates like differences in pressure which force the ball to shift and move in interesting ways, where there's different pressure pockets, and then it pulls the ball down at a faster rate, or causes it to, if you ever see like a, I think it's called a 12-6, or like like an 11-5, or it'd be, I think, a 1 to, basically the ball will rotate in a certain way, and that will cause it to move much more than it would based off of just natural gravitation. So Statcast doesn't have that data, or at least it's not publicly available. Like, there's a subscription that I don't have. So the only thing that we have to work with is the angle that it came off of the bat, essentially, and then the velocity at which it came off the bat. That's all we have to work with. So the air density estimate, that field is essentially a manual adjustment that I've made. And when we get into the calculations about resistance and drag, that is the manual adjustment that I made when I was crafting this data, essentially to adjust for Magnus effect, and then also what's known as the Coriolis effect, which with military snipers have to worry about that, because of how the rotation of the Earth will it affects the way that things move and rotate around the Earth as the Earth itself is rotating on its axis. So that's basically the adjustment to try and get it so that the final distance that Statcast measured so closely matches to the estimated distance that we project. So that's essentially what I had to do with this in order to get it to work, to kind of fine tune it so that when we apply air resistance, it allows us to more effectively model this and have it so that it's relatively close. So then we have some information about the pitch. So that's the Statcast data. And then we have a time interval where I've got 221 points. So it basically goes from 0 to 5.5 seconds in increments of 0.025 seconds, or basically 1/40th of a second. So that's the basic gist of that point in this data source. And what we're doing with that is we are using that to densify our data so that each home run has 221 kind of records associated with it, so that over time we're able to model out the change of the ball in terms of its velocity, its position, its acceleration or deceleration. And then the last component here is baseball images. Basically, you have your regular orientation of a baseball where it just looks like it's straight up and down. And then I have like every 20 degrees, it's rotated, and I just rotated it with Figma. And that is from, I think, Goodware via Flat Icon. So make sure that as you're doing the solution that you are incorporating a citation there. But that's what the data looks like. And if we look at what the function of this is, so here in Tableau Public, we've got our KPIs. And then when we play this, what happens is that the balls are, they're looking like they're rotating counterclockwise. But what's happening is that there is a point in time where the ball is, where we have a given velocity and a given position. And the position is what we're modeling. If we wanted to, we could model position, we could model velocity, we could model acceleration. But for the sake of this example, we just care about the trajectory. So that's going to be the thing that's displayed. So what we've got to consider here is physics in and of itself is a fairly straightforward science. There's a lot of just math and understanding what factors are at play. So in a world where we don't have air resistance or drag, the only factor that would come into play if you projectile model motion equations, what you'll generally see is you're just working with gravity, which negative 9.8 meters per second squared. That's the acceleration of an object absent of air resistance that you'd have to factor for this. So essentially what you're able to do with those different three factors is they interact and play with each other kind of in a way. because position is essentially an object's location in time. You can calculate velocity based off of two positions, and then if you have a distance between them, that's great. If you divide that distance that has been traveled, divide it by the time step, so in our case it's 1/40th of 1 second, then what you encounter is that you've basically done a position over time. So if we think about miles, that's a distance divided by time per hour, or meters, it's a distance divided by second, meters per second. So that's how you get a velocity. And then acceleration is basically taking that to another level, where you say, okay, I've got two velocities, velocity at timestamp 1 and timestamp 2. And what we're doing by calculating the acceleration is just measuring the rate of change of velocity, which essentially allows us to then calculate using the exact same thing, where we've got two changes in velocity divided by seconds. And that essentially, for most of our purposes for this, it is our meters per second squared, or meters per second, or velocity per second. So it's basically the rate of change in velocity gives us our acceleration. So got a bunch of different constants here that we're going to be using. The baseball mass, 0.145 kilograms. The cross-sectional area of a baseball, 0.00426 meters squared. Drag coefficient, this doesn't have any units as far as I can tell, but it's based off of basically a sphere. What would the drag coefficient be? And drag coefficient is, if you, I think Wikipedia searched drag coefficient by like shape. Different shapes have different coefficients for how much drag they induce as they travel through the air. So for a sphere, it is 0.4. And off of several different websites that I was researching as I was putting this together, the drag coefficient for a baseball is, for most means and purposes, generally referred to as 0.4. The Y position start, so we're assuming that it's not starting on the ground, because then basically Aaron Judge would be, he'd basically be golfing if we were going to consider it off of that. So it's 1 meter up, which he's a guy who's 6'7", so he's a big dude. We're going to assume that it basically, the ball is hit at waist high at 1 meter in the air, so basically 3.3 feet off the ground. And then the time interval, 0.025 seconds, 1/40th of a second. Some conversion rates for if we need to convert from miles per hour to meters per second, dividing that by that in order to get that, so on and so forth. Pretty straightforward stuff. So the order that we think about this in terms of solving it is that at a given point in time, we have a position at the start of a time step, and we have a velocity in both the X and the Y direction. So it's important to think about, okay, we have at the start, we have a given vector of direction, that's essentially the velocity, and then we have our position as we're starting. So then over the course of that time step, force is acting. The force, also known as mass times acceleration, F equals ma from a physics standpoint. Force is the drag or the air resistance, as well as gravity, that is imparting itself on the ball, and that is changing the velocity. So when the ball is initially hit at timestamp 0, at the instant that it's hit, post ball compression, basically, if we assume that the ball is struck and the ball immediately starts to move at its velocity. Air resistance goes from basically nothing, because the ball isn't moving, to now it's moving. Now we have this velocity. So the equations for gravitation, those are constant throughout, because all we have for the force of gravitation is the mass of the baseball and the acceleration, which remains constant. The acceleration, negative 9.8 meters per second squared. So what does change is drag, and that's kind of the tricky, nuancy piece with this. So the acceleration, the drag, slows down the velocity in the X and the Y X and Y direction. So the ball is decelerating as it's traveling through the air. So after a certain amount of time, as I kind of walk through position, velocity, acceleration, at that point in time, you have a velocity, an end velocity. which then if you know what your end velocity, your start velocity and your end velocity are, I think for the sake of my example, we have our ending velocity. We're going to assume that that was the rate of speed, the rate of positional change that the ball was going through over the course of that time, that 0.025 seconds. So then you have that velocity, and then you're saying, okay, we have that velocity, and in the X and the Y position, the ball was hit like this. At timestamp 2, it has moved at a velocity, and then you multiply that times the time step, and you can calculate based off of the prior position, how much did it climb, how much did it drop, how much did it advance forward, basically. So that's what the force component is, and that's kind of what the end state of it is. So once you know what your ending velocity is, you use that to calculate your end position, which just so happens to be the next timestamp's starting position. So you got a bunch of different fields that are kind of dependent on each other in order to get this to properly calculate. So in this example here it's perfect. We have our ending velocity times the time step, and that allows us to calculate what was the positional change, the rate of change of position, and then adding that to the starting position, and then that gives us our ending position. That's it. So with respect to position, what we care about, this is in meters for the most part. In the final dashboard, it's converted back to feet. So for the sake of this, we have our starting position at X of 0. So the ball is hit on the plate, and then it's 1 meter up, and then that goes in a certain direction, which we didn't get a directional variable from Statcast. So all we care about is once it's hit, what is its loft, what is its rate of speed exiting home plate. So we have our starting position, at each timestamp we have our start position for the prior step, or that starting of 0, 1, and then we have our end position, which is dependent on the velocity. So as I mentioned, starting position will equal the ending position of the prior step over time. So as mentioned, thinking about velocity then, so velocity, it's the rate of change of position. In the tooltips, there is an estimated velocity, and that is converted from meters per second to 2 miles per hour. And that's just kind of like a point in time measurement that's taking place. That's based off of kind of like the Pythagorean theorem of you've got a velocity in the X direction and in the Y direction. If you think about a triangle, right triangle, a squared plus b squared equals c squared. So essentially the hypotenuse is the vector of velocity in a given direction at a given point in time. But at time step 0, we have the exit velocity that's measured, and then what we have is the loft of the hit. So we have a launch angle, and using kind of the Sakatoa trigonometry, we can use cosine. We have to convert the launch angle, which is in degrees, into radians. We have cosine of the angle of launch and multiply that times the exit velocity. That gives us the initial velocity in the horizontal direction. And we use something very similar with sine to get that for our vertical. So I don't have the ability here to draw a triangle outside of in the air, but that's how you'd go about calculating given so this is the hypotenuse of velocity at time step 0, where you got your launch angle down here, and then you have your magnitude of your vector. You can break that into its X component and its Y component. So that's how that works. So then when we are trying to calculate our ending velocity, what we have is the force that's calculated, which is the combination of drag and gravitational pull. And if force equals mass times acceleration, and we're trying to calculate the acceleration, if we divide the force by the mass of the baseball, that gives us our acceleration. We take that acceleration and multiply it by our time step. That gives us the rate of velocity change. If we apply that change rate to our starting velocity, that gives us our ending velocity. So all of these things are kind of intertwined when it comes to position, velocity, and acceleration. But as I mentioned, 2 forces, drag and gravity. Drag has this calculation here. So that's where those parameters I mentioned earlier come into play. So we have a drag coefficient of 0.4, the air density, which comes from the data. It's the manual adjustment that I've made to things. And we have the cross-sectional area, which is basically if you're looking at the baseball from the side, it's the amount of area in meters squared that a baseball takes up, which is 0.00426 square meters, I think. And then you have your starting velocity at that time step. And at the starting of each time step, you do have that velocity. It's either the exit velocity in the X direction or the Y direction. And it's either exit the initial velocity, or that comes from the prior step. So that is essentially how we go about calculating drag in the X and the Y direction. And then gravity, that is the only thing that we care about. We have our mass times our acceleration, and that allows us to calculate the amount of force in, I think, newtons is the rate for force, and that remains constant throughout. So that one doesn't change. The two accelerations that will change are the acceleration in the Y direction and the X direction. So as I was going about calculating this, I ran into some interesting little nuances with circular reference calculations because I was referencing a function to itself, which you can't do. Most of the time you can't do it. There are certain nuances that I've encountered where you can, and it's interesting how if you have a dependency, you have to leverage previous value in order to get there and overcome it. Last component here. So I already mentioned Magnus effect and the Coriolis effect, but what we have to do is we have to be calculating the starting position, X and Y, the starting velocity, X and Y, and then we have to calculate the three different types of acceleration. We have the drag, X and Y, and gravity, Y. And that allows us to then calculate our end velocity, X and Y, which then that end velocity, comparing, taking that times the time step, allows us to determine the positional rate of change in the X and Y direction, which then we apply that to our starting position, which then gives us our ending position. And so all of these things kind of stack on each other as we're going about calculating this. So with that being said, that is a very long explanation for how this all works. And with that, let's jump in. I'm going to start with the finished product. Let me change screens here. So stop sharing and then reshare. Okay. So I'm pretty sure I'm sharing the right screen now, but essentially what we're working with here. So these KPIs, I've got a mask over this, but let's look at our data source. What we've got with our data source, we've got the two different key factors here. It's taking a bit to load because it's, I've got it connected to my Google Drive, so bear with me while that makes that connection. What's cool about the Google Drive is you can actually set up Google Drive to update data, but for the sake of this, I haven't been updating it with home run 63 and 64 for the postseason because we only care about the regular season. But here we go. So we have our home run data source from Statcast, this one here, and then we have the data densification. On data densification, we're just trying to apply each level of timestamp, and I'm just doing a really simple, string of A equals string of A. That's always going to be true. So it's always going to take the data densification piece, and it's going to essentially attach a timestamp to each record with that. So that's very, very simple data modeling piece, very easy to work with. So now we got our KPIs, which the KPIs are very simple. We have a count distinct of home run number, that's the number of home runs. We have our average distance. So if each baseball, if the distance that's in the data, if we did a sum, it would be 221 instances per home run. It's all going to be the same number of records. So we can just do a straight average, and that's fine. If you wanted to, you could probably do an LOD on this to say, by home run number, what is the minimum distance? Because the distance will be the same, but then you take a sum of that minimum, and that will basically give the exact same amount of 412. From there, you have the exact same thing about exit velocity. That's perfectly fine. Launch angle, perfectly fine. And then average pitch velocity in miles per hour. So some things that I would recommend as you're going about doing this is with your launch angles, setting your number formats, set them here. So for this, I've taken the degrees amount or the character for that symbol, and I've attached it as a suffix for that. For pitch velocity, doing the exact same thing, and that is just doing a space and then MPH. That way we've got the units that we need for this, and we're not having to manually type it in. So anytime that we're referencing that. So that allows us to have that the way we want. But if we dig into, so here we've got basically each home run being represented, and we're able to add a line here. So if I wanted to replicate this, you'd take your exit velocity, and then you've got your distance. And what's great about that is that you're able to just do a really, really simple scatter plot by home run number, and then you add in all of these fields, and then you edit the tooltip so that it reflects it. So that's the scatter plots are very simple. I have a shape scatter as a part of the bonus, and this is the formula that I did. So in order to have it apply randomly, I just did a fixed on home run number, take the minimum integer of a random value between 0 and 1, multiply that times 9. So I should get some number between 0 and 9, and then take the minimum integer of that, which should result, presuming that you didn't have exactly 1, you should get something between 0 and 8, which gives you 9 different values, which then you can assign those however you so please here. So that's how that kind of scrambles the orientation of the balls here with that. So that's that. And I think every time, because I'm using ran or the random function, it will actually update the direction and orientation of the balls as you make selections, which is kind of cool. So that's essentially how you go about and build out the exit velocity, launch angle, and pitch velocity factors here. A caveat to this, so for the different components, I wanted to ensure that as you do a filter, so you could just do the quick filter, and what that would have, what the impact that would have is that if you had those selected, it would also filter these charts, and you wouldn't be able to see any of the other values. So what we have here is that this is applying a dashboard filter with a filter action to the KPIs and to this chart. So it's filtering it down based off of the home run number. Between the scatter plots, there's actually a highlight action. So it's a select highlight action. So that when I select these ones, it's saying, don't filter them out here, just highlight the ones that you've selected. So that's essentially how that works, and it filters out the ones that we did not want displayed here. So let's get into the nitty-gritty meat and potatoes of the ball trajectory calculation, because it is a bit of a beast, and it took a while to figure out how to do it. So originally I modeled this out in Excel, and that's where I was able to figure it out, but it did take quite a bit of time to figure out how to effectively structure the calculations and work with them within Tableau. So what I've got modeled here is just the position start. So if you zoom this all the way back, or start this back at 0 seconds, and then let's do it fast. And let's, before we do that, let's just filter it down on 1, and then just get to this 1. So we've got 1 through the action there. If we go fast, we can see this ball get hit. And if I don't know how well this is recording my screen, but what you're able to see is the ball's rotating counterclockwise, and we're seeing the position of it basically change. Because we have one ball, we can see the reference lines telling us the position at a certain point in time. And once it hits the ground, it stops in that location where it stopped, and it keeps going all the way into the time interval. So with the time interval, we have that on pages, which is great. But essentially what we've got to do here is, let's jump into our position calculations. So position start X. If we think about this, Actually, let's start with our initial velocity. Okay, so initial velocity, these are the sine and cosine ones, where we have our exit velocity, which I just convert from miles per hour to meters per second, which it's just the miles per hour exit velocity divided by 2.237. That gets it to us at meters per second. From there, then we have our initial velocity in the x and y direction in meters per second. So that's it for that. Fairly straightforward. And that allows us to understand what we're looking at. So there we've got our initial velocity in the x direction, initial velocity in the y direction, and that will remain constant throughout the initial velocity because the ball was struck at a given velocity, and we apply that to all of the timestamp records, so that will always remain the same. But we only really care about that for the sake of the very first record of timestamp equals 0.0 seconds. So we look at our position start. If the time interval equals 0, x equals 0. Otherwise, if the previous end position, if that y position is greater than 0, then take the previous x and reference that to pull it into the start. Otherwise, in the event that it is negative, look at the previous value within the column. So that's what prevents it once you hit the ground. The ball was hit at 1 meter above, goes up, comes down, hits the ground, positions at 0. Then what it's going to do is it's going to say basically reference that height, reference that position, and then keep that constant throughout the rest of it. That's position start x, position start y. It's very similar. I've parameterized the y position start, so if we wanted to have it, at 0.75 meters, we could adjust it, and now all of these calculations would adjust based off of how it's calculating it. So doing the exact same thing. If the time interval equals 0, then position start at 1 meter. Just do this. It's basically 3 feet, 3.3 feet if you look in the height of the tooltip. And then it's doing the exact same thing, where it's saying if the position for the y and the most recent time step prior to this was greater than or equal to 0, then pull in the y, otherwise 0. That's what it's doing. So that's for position start. If we look at velocity start, so here what we're doing is we're applying the drag component in the x direction only, because we don't care about gravity in the x, because gravity isn't affecting that. We have our initial velocity, which is calculated, I think, in the x direction with cosine. But what we have is if the time interval equals 0, if it's the very first record, reference the initial velocity, because that's what a velocity should be the moment that the ball is struck, assuming no compression. So what we're doing is we're saying, take the previous, in all of the cases outside of timestamp equals 0, reference the start velocity in the prior record, and then we're going to figure out what the drag force is. That's the drag force. We're just taking our drag coefficient, that's a parameter. It's taking our air density estimate, which varies by ball. We have the cross-sectional area, which is a constant. We have the previous value, which previous value is the starting velocity of the prior, or that's correct. We're taking that start velocity, squaring it, and taking all of those factors and multiplying them together to get the force of drag at a given moment in time, at a given velocity, and at a given air density, essentially. Force equals mass times acceleration. If we want to get the acceleration, we divide out by mass. So we divide it by the baseball's mass, and that gives us the acceleration in the highlighted section here. Multiply that times the time step, which you could use as a parameter here, or you could do a number of different ways here to get it. I just have it written out. Multiply the acceleration times the time step. That gets us our change in velocity. take our previous velocity at the start, add on this change velocity, and that's getting us essentially the it's the exact same thing as our ending velocity of the previous record. So if we look at our end velocity, these functions, we have our x velocity in the x direction, we have our drag force, we have our baseball mass, and we have our timestamp change. The drag force is that cross-sectional area piece that we had highlighted. And it basically, for all intents and purposes, this exit velocity piece isn't really ever used. So we can reference the previous value function instead of like a lookup -1 on itself, which wouldn't work. That allows us to calculate the what is the starting velocity at a given point in time. So that is how that essentially works. If we look at the y velocity, this has a extra caveat to it. So if we look at, we have two forces in play here. So we have the force due to gravity, and then we have the force due to drag in the y direction. Because drag is part of what is slowing it on its way up and on its way down. It is slowing down the normal velocity of it. So here we have the exact same thing. We have the initial velocity in the y direction. So you get the ball, it's hit this way. You have a y direction that goes with that, and then you have the x direction that we talked about earlier. So here we say, what was your previous y velocity? Take that, so that's basically the previous end plus whatever forces are applied to it. So we take our starting velocity, then we focus our forces together, because you can have two forces that are in the same unit of newtons. So gravitational force, which is just the baseball's mass times its acceleration, and then we are basically adding it, or since we have a negative coefficient here, we're subtracting it essentially. We have the exact same thing, but now this previous value is focused on the velocity starting in the y direction. So we take that, we compute that, and that is what allows us, when we divide it by the mass, multiply by the time step, that gets us our acceleration in that direction. So that's essentially how that goes about working. Now what we need to do is, so we have our position start. So we have our position end, which for all intents and purposes, what we care about is the position start in terms of what's displayed here on the model. Position end x, we have essentially our, in the x standpoint, all we care about for timestamp 0 is what was the ending velocity times 0.025, and that gives us the amount of change that took place in position for that first time step. Everything else, we're just taking that previous x position. So the ball is slowly moving in the horizontal direction. It starts out fast, and then it slows down as drag applies on it. So here with this, we have the previous value. So what was the previous position of this ball in the x position, plus the ending velocity, which that essentially gets us the exact same function here. But we're just taking that, because otherwise what you would see, if we didn't have this previous value part, you would see it basically would plot it out at a certain point, and then as drag impacts it, you'd see the rate of change would get closer and closer to 0 until the ball eventually stops. So that's how you calculate position end x, position end y. We have our y position start plus our rate of change of velocity for that first step. And then we're essentially doing the exact same thing with that velocity and y component, where we only care about the y component. As we go to build this, you have to think about the different components that are on the view. So we have the time interval and the home run number. Those are really the one dimension that really works, that we care about, is the home run number, because that's what differentiates each ball, each of the 62 different marks that are on the card. So the shape rotation, that's essentially looking at the, let me show that. shape rotation is saying we have a ball with basically the position, if it's less than or equal to 0, which we fix that so the ball doesn't go below the surface of the earth. If it is less than 0, then set the position to the orientation of it to 0 degrees. Otherwise, take the time interval, which is in 40ths of a second, do a modulo operator on that to basically factor it out by 9. And then from there, we multiply that times 20. That gets us our basically 1 through or 0 through 9, which we can then convert into our different orientations in factors of 20 degrees. So with that, we basically then apply that, and if you import your shapes, basically then you assign the palette. Make sure that the orientation is correct, just because I had to manually assign some of these. So just make sure that the rotation, when it plays through in the time step, it looks like it's rotating. But that's an extra bonus thing. You don't have to do that if you don't want to. So as we're setting up the pages, we move this forward. We have our X and our Y start positions at the time step. We take time interval and drag that onto pages. And as we're setting up these pages, so if we have marks, marks only, if we do both, which we have, so there we go. So this is essentially, if you just had marks, what it would look like as you played it, which is actually still pretty cool. But you can see that the original position of the ball is fading, but we don't really care about this estimated previous position after a certain number of seconds. For the sake of this example, we don't care about that. All we care about is the trail, which the trail, you're not going to be able to hover over it and get those little points in time. Because at a certain point in time, if you're comparing multiple home runs, if you had all 62, it would essentially be plotting all 62 home runs times the number of timestamps that have elapsed. So you basically get this big, in that case, it was a big black blob trailing all of these home runs, which doesn't really allow you to compare them or focus in on a specific one if you're comparing a really, really high pop-up home run to a really shallow thing that's basically coming out of a cannon. So several different things here. But with the time interval, that allows you to really focus on one mark if you do trails only, which, for the sake of that, I've just got 50% transparency on this, the bottom left gray box, and doing just a regular a line there. For the sake of design, if you wanted to have it be lighter, you could do whatever you'd like for that. But doing the length of all, you could, kind of a cool thing I played with as I was developing this is, let's say we wanted the last 15 shown. You could essentially play this, and you can see the ball, and it looks like it's got a tail to it. So you could do that if you want to, but for the sake of this, we're just going to do all. So that draws the entire path or trajectory of the ball over time. So as you configure this for the position start X, there are nested calculations here. And what we want to have happen with each of these different calculations with position start, position end, X and Y, and then the velocity start in that given direction, you want to ensure that the home run is deselected. So it's basically going to group it by that. If you didn't have time interval here as a dimension, you'd essentially have nothing checked. So for instance, if we pull this off, all of those are going to break. Oh, it didn't. Fantastic. I thought it was going to break. So here what you'd have is all of these table calcs. I'm surprised that it's still checked. Okay. Interesting. I would have expected it to break there. We'll put it back because we use it in the tooltip after a certain number of seconds have elapsed. But for each of these different table calculations that are referencing, because you're using either a lookup or you're using previous value, you select your time interval, which is that increment from 0 to 5.5 seconds in 40th of a second. And you deselect that home run number, and this essentially allows you to properly define the scope and direction of the table calculation as you're setting it up. One thing I would recommend is, as you're doing this, actually build out a table, because that table is going to allow you to see the changes and ensure that your numbers are correct. So with that, I think that's essentially it in terms of how you go about building out this dashboard and building out the calculations and thinking through that logic that comes with it. I do realize that this challenge, when it's all said and done, this challenge was a bit of a monster to put together, because it is pretty complicated when you think about, okay, we're calculating rates of change at points in time, and then we're taking that times a time step to convert an acceleration or convert a velocity into either a velocity or a position respectively. So my name is Sam Epley. Thanks for tuning in. If you have any questions about how I went about doing this, please let me know, and have a great rest of your day.